Hi, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're really moving right along here, and we just looked at the Milky Way and the types of galaxies in the cosmos, and then we looked at the interacting galaxies, and we mentioned that galaxies are really big compared to their sizes, but we also saw that galaxies in the distance are really, really far. And I asserted in the previous lecture that in the interacting galaxy images that we saw, that huge number, we saw lots of little galaxies at extraordinary distances, and they gave numbers like hundreds of millions of light years or billions of light years distant. So really, nobody's ever been there. So how do we know those distances? And basically, now we're getting close to the beginning of the study of cosmology. Cosmology is the study of the entire universe, and we're going to be looking at the physics of the whole universe, how things are distributed on big scales, how things move on big scales, how the universe has changed from the beginning of time to the future, and what the age of the universe is, how it began, and what ultimately it will become. So cosmology is broken up into four big pieces. There's four pieces, but I call zero homogeneous isotropy because it's kind of a zero thing as its underlying assumption. And we're going to look at mostly number four, and getting to know number one. Number one is redshift, which is the key way that we know of distances in the Big Bang. And again, we always must remember that the cosmological principle says that there's really nothing special about our location. It's just our home. That makes it really special because you can't quite live on a white dwarf, and you can't quite live on Mars yet. I mean, maybe someday Elon Musk will take us there. And we don't live on Pluto yet. We can't travel between the stars yet. So our place is our home right now, and that makes it special. But we apply the idea that really the laws of physics must be the same everywhere that they are here. So with that idea, and we look around on the cosmos, the cosmological principle says there's nothing special, meaning we're in no other different place. But yet you notice that when we look in the sky, we see that basically everything in the sky is roughly the same thing in every direction. It's called isotropy. And if you combine it with the cosmological principle, it says that nothing's really special, then isotropy isn't really that special. So therefore, everything is pretty much homogeneous everywhere. And so that means anybody on any galaxy ever seen by anyone, if they have people out there on those distant stars, then they would see the sky roughly the same way we do. Maybe there'll be more galaxies, maybe less. Maybe there'll be more supernova, maybe more gas, maybe less. But they're going to see galaxies, they're going to see supernovae, they're going to see stars and planets like we do. So it's going to be the same stuff. So now we're going to look at how we know the distances to the galaxies. And so we start from the idea of Hubble's law. And Hubble's law is something very interesting that said, wow, we're going to get to it next time, really the detail about Hubble's law. But basically, Hubble's law relates the distance, d, to the recession speed of the galaxy, how fast its redshift indicates it's rushing away from us. And so it's proportional to, the distance is proportional to the speed v, the speed that's rushing away from us, which is inversely proportional to the Hubble constant, which is h naught. And that is for nearby galaxies. And for nearby galaxies, we can simply measure what's called the redshift. And the redshift is z. And z is the shift in the wavelength of light from its rest wavelength times the speed of light c, divided by h naught. So the trick is we've got to figure out how to get this h naught number, because how do we know what the heck it is? All right. Our goal is to find this magic number that gives us the distances to the far, far galaxies. And we'll just describe its origin next time. But there's no real way you can get it universally. I mean, it begins with extraordinary expansion, as we'll see next time. So we're going to look at the way we get up to redshift. And the idea of redshift was known for a long time, since the 1920s. That's how Edwin Hubble determined how far things are. But we're going to look at that more carefully soon. But there's no one single distance method that gets you everywhere across the entire universe. Some things are good for close things. Some things are good for far things. Some things are good for really far things that aren't really too far. And so we call this a bootstrap process. You pull yourself up by your bootstraps, and you get yourself out the door. So we find distances to near objects, and then you find something like that near object at a farther object that encompasses it or is next to it, and then you calibrate that you find some new way of seeing something that's farther and presumably brighter and easier to see than the thing that was closer that was relatively dim and can't be seen from so far away. The trick is, though, and this makes it really problem, is that errors get made. Mistakes are made. So let's look at the nearby thing. Way back, we talked about Henrietta Leavitt's luminosity period relationship for Cepheids that she discovered. And that is one of the most important relationships, but it can only get you about 100,000 or so light years, or 150 million light years or so. And that's if you use the Hubble Space Telescope. But that's hard to do with the Hubble Space Telescope because you need lots and lots of time, hundreds of Hubble orbits, and that means you have to have one of the best reasons ever to actually go hunting for Cepheids in some really distant location, because the Hubble Space Telescope is an extremely expensive thing to run, and people don't give up their orbits very well, and you have to put in a decent proposal so that you can push people away, because there's only so many times that the Hubble Space Telescope can orbit the Earth in its lifespan. So use it wisely. Finally, Cepheid relationships only really work for spiral and irregular galaxies because that's where the star formation is going on. You got to have young, hot stars in order to make Cepheids. And so the farthest you can really get with Cepheids, since you can actually try to identify individual Cepheids, is about the Virgo cluster of galaxies, which is about 60 million light years away or so, 65 million light years away. That, at 65 million light years away, is very nearby in terms of the universe. All of the galaxies that we looked at in those interacting things are within 10 to 20 up to 50 or 70 or less than 100 million light years away. And the things in the background were much further. So really we're trying to get to the grandest size scales, how we can know things that are billions of light years away, not just millions. So here is what we call the cosmic distance ladder, where we start with parallaxes, and use proper motions and main sequence fitting or cluster diagrams. Hyades is critical. Cepheids and Lyrae get you out to the Large Magellanic Cloud and out to Virgo cluster with the Hubble. And then you have something called the Tully-Fisher relationship and Type 1a supernovae and other bright objects, which get you out to the Coma cluster, which is about 10 to the 8th parsecs. And then finally, you can really start calibrating the redshifts out there. All right, so our first step is measuring the astronomical unit, and we talked about this many times in the past. The AU is the average or mean Earth-Sun distance. It's about 150 million kilometers, and you measure by geometric triangulation. You bounce some radar off of Venus when it is at quarter phase, meaning you see Venus as half illuminated in the sky, and that means it's at a right triangle with respect to the sun, and so you get an angle between the sun and Venus, and that's not 90 degrees, but the angle between that the sun and your Earth make with respect to Venus is 90 degrees. Bounce some radar off of Venus because it's very reflective. Get you a distance to Venus. You can use high school trigonometry in order to get the distance to Venus. Now, Copernicus and many others have determined that the orbits of the planets have relative sizes, and you can look at the size of the orbits and their relative things and get all their relative distances. So the main thing to measure is the astronomical unit, because once you get that, then you can get the relative distances to all the planets. And if you determine the astronomical unit, you can get the trigonometric parallax to stars. And once again, way back, we talked about trigonometric parallax. You got to know the astronomical unit, which is the radius of the Earth's orbit around the sun, and that allows you to calculate those little tiny angles that stars seem to make as the Earth goes around the sun in a year. Remember that the typical parallax is always less than 1 arcsecond, and an arcsecond is about the same size as a regulation NFL football held 37 miles away. So that's a really small angular size. So the nice thing is that stellar parallaxes recently got a huge burst at 2016 with the first release of the Gaia dataset by the European Space Agency. And they've released their second data set recently, so there's lots and lots of data. Up until then, it was just ground-based stuff that got you out to about 100 parsecs, and Hipparcos satellite, which only got to about 1,000 parsecs. And now, with this data, you can get the absolute distances to things. If you can get absolute distances, you can use the inverse square law for brightness, to get their luminosities. And so we can use that to get spectroscopic parallax. So what we do is we find typical clusters of stars, and the prototypical cluster is the Hyades cluster. And we make an HR diagram based on the difference in brightness in two colors, the B minus V, and two different filters, and compare it to the brightness seen in the V, that's a standard color magnitude diagram, or HR diagram. And the shape that it makes is the Hyades has a distinct main sequence, and we figure that all stars are the same in the cosmos. So if a main sequence is below another main sequence, that's because it's farther, not because it's a different kind of main sequence. No, it's just that it's farther. Maybe it's made up of a slightly different population, but that population would but that doesn't account for huge differences in the HR diagrams. The major differences between the brightnesses of a full HR diagram between two clusters is because of the relative distance. And so diffraction limited viewing gets you out to see star clusters out to the Large Magellanic Cloud, which is about 100 kiloparsecs away, or thereabouts, and you can get to, and you can make out, and that allows you to be able to make out individual stars. You have to be able to make out individual stars in clusters to create an HR diagram. And roughly the distance of the Large Magellanic Cloud is the length. Now, it's good that the Large Magellanic Cloud is there because it has a huge amount of star formation going on. And because it's got a lot of star formation going on, it's got a lot of young clusters. If it's got a lot of young clusters, it's got a lot of Cepheids. If it's got a lot of Cepheids, then you can calibrate the Cepheids from that. So this is really good. So now we can look at the Cepheid variables, which are the next step up. And the Hyades gives us the basis for all star clusters, because now you can get the physics of the star clusters and you get the absolute brightness, because you can get because the Hyades are only about 150 light years away. And then you can use the Hyades to get other young clusters. Remember that Cepheids are supergiant stars. In young clusters, they're about to die. And there are tons of these clusters, as I said, in the Large Magellanic Cloud. And since the LMC, once you're 200,000 light years away, 1 or 2 light years back or forth doesn't really matter. So what you do is you look at all the star clusters that you can find in the Large Magellanic Cloud, make a generic HR diagram out of them, and then fit that HR diagram to what you see for the Hyades. And if you can do that thing, then you can get the relative distance to the Large Magellanic Cloud. And if you can get that, then you can find specific Cepheid variables, which are much brighter than most of the stars in any of the clusters, and that allows you to match it up. So then you can get a calibration for the Cepheid variables. So these are so bright that they can get you out even farther than is possible with main sequence fitting. And so, but the thing is that you can only really get out to about the Virgo cluster of galaxies with Cepheid variables. That's about 60 million light years away. And you have to look in spiral galaxies because, there's got to be star clusters and there's got to be formation going on. Ellipticals don't have star formation, so you ain't going to find Cepheids. Funny thing is, though, is that spirals aren't as bright as the brightest ellipticals, and ellipticals are far more numerous. Okay, so there's our standard thing. The Large Magellanic Cloud is littered with them, and we've got to find more. Finally, next we keep going up in scale, and we're starting to get a little desperate now because, things that are really bright that can be seen for 70 or 80 or 100 million light years away, those things are pretty rare. They're by definition rare, but you got to take what you can get. And so maybe you can find type 1a supernovae, which are standard candles of some sense, because they happen in a very specific way as the star explodes, because the white dwarf explodes because it just gets 10 extra atoms of hydrogen on it and explodes exactly the same way each time. So therefore it's a type of standard candle. Now you can also get a relationship for planetary nebulae, which are the shells of dying stars. So the brightest planetary nebulae are probably at roughly the same brightness because they all come from roughly the same kinds of stars. So if you find bright planetary nebulae, you can make a relationship for their rough luminosities and get something out of that. Also, you can say, well, what are the distribution and sizes of globular clusters in the Milky Way? And by studying globular clusters in the Milky Way, you can determine roughly how globular clusters go in terms of their luminosities. And so hopefully you can make out something with that. That's all some tricks though, but the real thing is we got to find Cepheid variables to get to spirals and hope you can find something in there in that spiral that helps you. So these things mix and match and max and niche, and basically Cepheids are the most important thing. But the good thing about getting out to the Virgo cluster is it starts to the very beginnings of getting us a local estimate of the expansion rate of the cosmos. Now the Virgo cluster is approaching, the local group is approaching the Virgo cluster, so it's a little tricky and you got to take into a lot of motions and things like that, but we're getting close. Now then we can do a new thing, is once we have a distance to the Virgo cluster, we can assume that galaxies are similar objects to nearby ones. Remember when the Herschels did star counts? Well, people do that with galaxies too. And we assume that certain kinds of galaxies are certain kinds of luminosities, and it gets kind of dicey. But if you look at enough of them, you can find correlations between luminosity and some distance-independent property. And large samples also help you remove the Doppler effect due to redshift of the motions of intrinsic galaxies during their space. And that's called their peculiar motion. Finally, there's two major things that are looked at, and they're called, one of them is called the Tully-Fisher relationship for spiral galaxies, and it's found that spiral galaxies have a luminosity that's related to their rotation speed. And you can use 21 centimeter radio emission in order to determine the rotation rate. And that's a very specific wavelength, and it's not littered with a bunch of other stuff, and 21 centimeter is pretty bright and can be seen for a very great distance. Also, there is a relationship in elliptical galaxies between the absolute luminosity of a galaxy and the line widths of the absorption features inside of the elliptical galaxy. So you can measure the absorption line widths of the spectra, and the absorption line widths are a measurement of the random motions of the stars in the elliptical galaxy, and the more random motions there are, the broader the lines. The broader their lines there means more motions, which means that there's more gravity. If there's more gravity, there's more mass, so you can determine a relationship between, if there's more mass, then there'll be more luminosity. And if you get an HR diagrammy of a kind of a population 2 sort of thing with all these ancient galaxies, then maybe you can make a relationship between the width of the absorption lines of an elliptical galaxy to its absolute luminosity. And that's also how we get the large mass differentials between them as well, is by looking at this particular relationship. So let's go back to pretty pictures, because pretty pictures are always fun. This is a wonderful image of the Virgo cluster of galaxies, which is in the constellation, of course, of Virgo. It's about 70 million light years away. But let's zoom in on the center of it. And if we zoom in on the center of it, we find we have a couple of ellipticals, but we have a few spiral galaxies. And those spiral galaxies, we can measure their rotation speeds. And why do we measure their rotation speeds? The faster they spin, the more massive they are. The more massive they are, the more stars they have. The more stars they have, the brighter they are. This particular thing only works with spirals, and the Virgo cluster has a number of spiral galaxies. So the Tully-Fisher relationship, which is a distinct relationship between the rotation rate of a spiral galaxy seen edge on and its luminosity, therefore its mass, is actually something that is very important in looking for distances to clusters of galaxies and individual galaxies too. So the Tully-Fisher relationship works for spirals, and all of these spirals can have their distances measured in this similar way. And we have, of course, our face model from whatever magazine, finding that in 21 centimeter radiation, exactly what happens, how do we measure this thing, is that the spiral galaxy, the hydrogen gas, is emitting at a specific wavelength of light. And each of the three little graphs shows the wavelength that it's emitting in a narrow band. However, if it's approaching us, if it's in a gas cloud that's approaching us, the frequency of the 21 centimeter radiation will be blue shifted towards a shorter wavelength. Maybe it's 19 centimeters. And if it's in the center, it will be unshifted, so it stays at 21. And if it's redshifted, maybe it's 25 centimeters or 23 centimeters or something like that. And the greater, and so when you add up the entire thing, you can't necessarily make out the entire galaxy unless it's very nearby, say in the Virgo cluster. Then you can say, oh, this is a spiral galaxy. It's got a really broad emission line. If it's got a broad emission line, because you add up all this stuff together, then you see that it must be rotating fast. And the faster it's rotating, the brighter it is, because the brighter it is, the more massive it is. The more massive it is, the more stars it has. And for spirals, that means bright stars and O and B type stars. All right, so the Tully-Fisher relationship is probably one of the most important relationships that is used for cosmic distance studies, because they're very, very bright. You don't have to wait for serendipitous things like supernovae, and you can't try to hunt out and scour out a whole bunch of tiny little point sources like planetary nebulae or bright supergiants or something like that. No, you just say, find me some galaxies. I'll take their rotation rates and I'll try to get a relationship between them. And so Tully and Fisher made a lot of hay out of this thing. And so all you have to do is calibrate it with a whole bunch of different relationships, and utilizing the distance to the Virgo cluster and calibrating the Tully-Fisher relationship using that. And then all you do is say, okay, what's the rotation rate? And determine that the faster it's rotating, the more massive it is. The more massive it is, the more luminous it is. And so we can get the luminosity in terms of comparison to the sun. All right, once you've calibrated the Tully-Fisher relationship, you may keep going further to find things that are even brighter than spiral galaxies, because maybe that 21 centimeter line is dim or fuzzy or hard to find. And those things are like a type 1a supernovae. And with all of that, then we can finally get out probably to redshift, and all these things get you about 1 billion parsecs or a gigaparsec. And the last thing you're hunting for is redshift distances. Redshift is the thing that comes after everything else. So remember, each one of these steps was calibrated on the feet of the one before it. Each step depended on accurate measurements of the one before it. And so you're trying to measure that finally, if you can get accurate distances to far galaxies, then if you can measure their redshifts, we find that the farther away the galaxy is, the greater the redshift it is. So we can then estimate, like we had that equation right back at the beginning, where we said, what's the distance? It depends on the speed with which it's rushing away from us. And in nearby galaxies, out to a few 100 million light years, maybe half a billion light years, it's pretty much a linear relationship like we saw. So the Hubble relationship is a measurement of the expansion rate of the universe. And so all we have to think now is that the redshift is a good distance indicator, because the farther away they are, the faster they're rushing away from each other. And now once we've calibrated the Hubble relationship, we can then measure things, the distances to very far galaxies, simply by taking a spectra and seeing what the redshift is. So all of these things are critical measurements. And of course, the most critical distance is to the Large Magellanic Cloud, which calibrates the Cepheids. And the Cepheids then get tweaked because maybe we find a type 1a supernovae floating around. And that's really important because those are extraordinarily bright beacons that can be seen up to billions of light years. And since it's about not Doppler shifts, we have to actually understand how galaxies are moving in space, because we need to study, because they're not just standing still, they are moving. Like the Andromeda Galaxy and Milky Way are going to collide in 4 billion years, in about 4 billion years. So galaxies are on the move, and that can add to the Doppler shift. So the nice thing to know is that lots of different measurements and lots of different ways to calibrate the redshift relation give almost all the same results between 60 and 67, 69 kilometers per second per megaparsec. Therefore, what this means is every megaparsec, every 300 million light years, 3 million light years, every 3 million light years, a galaxy is rushing away maybe 70 kilometers per second faster. 6 million light years, it's rushing 140 kilometers per second away. At 10 million light years, it's rushing, 30 million light years, it's rushing 700 kilometers per second away from us. So the faster it's rushing, the farther it is. And what's nice is there's many ways to measure this, and they're really close to each other. So here's some recent stuff, the most recent major work that's been done. The first was in 2012 by the WMAP probe, the Wilkinson Microwave Anisotropy probe, and they quoted the expansion rate at about 69 or so, plus or minus 0.8. So you can see what the error bars are. It just demonstrates how well they know their data. And so that's about 69-ish or so, and it's pretty good, and these are incredible measurements. We're in the era of precision cosmology. David Spergel would get mad at me for calling it pretty good. This is an astonishing achievement with the WMAP. And then European Space Agency's Planck mission came along and did some revisions and made some tension with that by quoting something in 2015 of about 67.8 or so, and that's really close to the WMAP, but there's some tension there. And then finally, the Sloan Digital Sky Survey looks at various things. It looks at galaxy clustering, and that helps how galaxies cluster is also affected by the expansion rate. It came out in 2016, and they give something that's very, very close to the Planck mission. And finally, there was a really good measurement that was done by looking at gravitationally lensed objects. And then gravitationally lensed objects show how light has moved through space as the universe has expanded underneath it on lines of sight. So the Holy Cow group, and yes, that is the exact name of the group, is called Holy Cow. You can go look it up. It's really wonderful. In November 2016, gave a rather large number that was well outside the error bars of everybody else. And that provided a little bit of a tweaky problem for many people. And at the January 2017 meeting of the American Astronomical Society, this was a major source of concern for a lot of people. But the thing is that they're all in really close agreement. We're no longer in the time where I was when I was in college, where people didn't know if it was 50 or if it was 100, and it was off by a factor of 2. Now people are getting really, really close with these measurements, and numerous teams are getting numbers that are very close to each other. But this means that we're in the era of precision cosmology, where we'll actually discover the expansion rate. And maybe it's dependent on direction, maybe not. But these measurements are very good and show that the expansion is robust and can be measured in many different ways. So we have really big questions that we're going to be asking in the future. And exactly what is the Hubble parameter? What's the expansion rate of the universe? What's the age of the universe? How did it expand in the past, and what will it go to in the future? And next time we're going to be talking about what is this redshift Hubble parameter thing anyway to begin with? Because I just talked about it like you knew about it, and you probably might have heard about it, and you might not know anything about it, but you're about to learn something about it. So stick around, and you'll see you'll learn about the redshift next time.